we are going, the data I sent to you, we are going to try the normality of it and then check which test are we going to use. So when we finish with it, I will start with the parametric side, then we go through them. And then when we have time, then we go through the non-parametric. So at this point, whenever you are doing any data analysis, after checking the reliability and the normality, then you just run your basic descriptives that are needed. So the next most important thing you have to do is to do the normality test. Because if you did not do the normality test, and then you move further by running maybe t-test, ANOVA, correlation, regression, the question is, why have you chosen that particular one? So because of the question why, that is why you have to do the normality test. So that to tell the person the data is normal. And once the data is normal, we have to use the parametric. But that one will be based on your objectives. So now let's switch to the data I shared with you in the group. Let's switch to it and then see how we tried our normality. So I'm sharing the data. Please, can you see the data shared?
Yes, please.
Okay, thank you. So now, for us to do the normality, we always consider the forgive me, the quantitative data which are in the form of numbers, numeric forms. These ones are qualitative data. We have coded them, but these ones are direct. So I share the data with you. Maybe in your free time, you can try. Please, before I forget, have you tried my homework? If you do, you can send your assignment to me privately so that I check. If it is okay, I comment it for you. If it is not, I correct you. So now let's do our normality test. For you to do the normality test, we are going to check the income and weight, whether they are normally distributed. This one, I'll give you the output later. I prepared this data myself. So I'll give you the output later. So this one is not like someone's research. I prepared the data myself. So when I'm done, I'll share the output with you. Because of that, I've not run the analysis yet. So let's start with the income. We are going to check if the income of these particular people is normally distributed. So what we do is we go to analyze, and then you choose descriptive statistics. Then with the drop-down menu, you choose explore. Then when you do it this way, the dependent list, that is where you put your test value. And our test value, we are going to test the income. So we select the income and then use this one. When it enters, we don't do anything here. We don't do anything to this one. We don't do anything here. And then what we do is we come to the plots and then we click. So what you do here is uncheck this one, the stem and leaf, and then check histogram. Don't check the stem and leaf. By default, it will put it on stem and leaf, but don't check it. You have to rather check the histogram. And then come down here and check normality plot with thesis. And then you check that one. Then after that, you say continue. So you finish with the process. Then you say, okay. With the okay, you should be able to see the output. I'm not sure you will see the output. Let me reshare the output. Please, can you see the output?
Yes.
So now this is our output. You don't need this one. You don't need this one as far as the normality is concerned. So what you do is, these are descriptives. So you don't need them for now. What you do is, you come to the normality test here. So what I always do is, I have to come to the histogram. Now this histogram here, by merely using your eyes to check, you will realize that it has the longest of its tail to the right. That means income is not normally distributed. The lower income is being, majority of the citizens are having the lowest income, whilst few of them, very few of them are now earning high income. And this is normal in our society. When you just come to, like, let me use Ghana, for example. When you get to Ghana now, majority of the people are taking their salary around 1,000 Ghana cedis, which is very low. They barely survive in it. So let's say those are the people here. This is the lower income. But when the people, those that are earning like 50,000, 60,000 within a month, just very few of them. And that is what you are seeing here. So the more the income grows, the lesser the people. So this one may be about how many people. This is the frequency, the number of people. So at the lower income, you see a lot of people earning it. But as the income keeps increasing, the number of people that are earning that income keeps decreasing. So income is not normally distributed. So when you look at this one, it tells that it confirms this one. It confirms this skewness. It confirms that it is positively skewed. And for that matter, you can use parametric tests. So that means if you want to do anything about it, you have to come to this side and then work with it. So when you use these assumptions here, any test within the parametric, unless of course you decided to transform the data. Otherwise, when you use anything within this particular range, that means your research is invalid. And that is the essence of the normality test. So aside the histogram confirm checking it, then we also use the statistical evidence. So we have Sid our Kolmogorov. So Kolmogorov, this one, the difference between the Kolmogorov and the Shapiro is that if the data set, even though they don't usually take notice of that, but at the normal circumstance, if the sample size, this one, the sample size is 200, but if the sample size is 50 or less, that is when we consider the Kolmogorov Smirnov. And if the sample size is more than 50, that means 50 and above, it means 51 and above. This one is up to 50. But when it is 51 and above, the best test is the Shapiro-Wilk. So now, when we check the Shapiro-Wilk here, we notice that our p-value, the significance value here is what we consider as the p-value. So it is less than 0.05. And we said when the value is less than 0.05, it means the data set is not normally distributed, which means that it has confirmed what the histogram here is saying. And for that matter, your further analysis should not be based on parametric, because the parametric tests are for normal distribution, not for other way around. Please, did you get the concept? If you did not understand anything, you can draw my attention before we move further. So now, this is basically how we do the normality test. We have just finished for the histogram. Now let's see, sorry, for the income. Now let's take the other one. I think weights. So let me
Hello.
share the,
Yeah, hello.
hello.
Yeah, please, can the statistics there also tell us something? Because we could see that standard deviation is more than the mean. Or it doesn't. Standard deviation, okay, it's less than the mean. Okay, okay. Or it doesn't tell us anything.
Which one?
The the central
This side.
tendency is there. Yes.
This side.
Yes, please.
The mean and the standard deviation, they are just the descriptive. So it's telling us that this one here is telling us that when we put all the incomes together and distributed them equally, each and every one is supposed to get like 4,700 and, sorry, 4,074 cedis, 0.12 pesos. So that is it's just describing the mean, like when we put all the means together and distributed among the people. But the standard deviation here is now telling us the spread of the income, which means that a lot of people like within this income are not closely, which means that others are earning far, far more than others. So because the spread here, the lower the standard deviation, the closer their earnings, and the vice versa. And this standard deviation here is very high. So that means that when we go to, let me go to the data and show you something. So when you check here, you could see some people are taking 4,266. Others are taking 6,000. And then let me do the descriptive so that we can see the data very clearly. We go to analyze, because if I'm reading it through this way, you wouldn't get it. We go to descriptive analysis. So we use descriptives. We just want to see how the data behave. And then we come to option. We already have mean, standard deviation, minimum. So now minimum and the maximum. That is very important. So we have to use it to check how the data is being ranged. So now when you come here, can you see the output?
Not yet.
Okay, I'm resharing. Can you see the output now?
Yes.
Okay. So now this is just the basic descriptives. You could see that the mean is this and then the standard deviation. But now see some people, someone is earning 875.41 Ghana cedis, and another person is earning 23,264. That means there is much spread in the earning. So the earnings are not very closer. This one is not, when you put this one, if you multiply it even by 10 or 20, you will not even get this one. So the spread is too much, and that has made the standard deviation being very large. The mean here is just trying to tell us that if we want to assume the same value for all of them, then each and every one is supposed to be earning this. However, there is much spread in the distribution of the income. And that is what we are experiencing in our various society. When you go, someone barely gets 100 cedis to spend, but another person is earning like 5,000 a day. So that is basically how income is being distributed. So now let's take our weights to check. So we go back to the data set. We are the data set. So we want to check if the weight here is normally distributed or not. We go through the same procedure as we did for the for the income. So we go to analyze. we select descriptive statistics. And then we select explore. So now our interest is on the weight. So we select the weight and push it here. Come to the plot and then select the histogram. Uncheck the stem and leaf. And then come here and select normality plot with thesis. Then you say continue. Then you say, okay. So we have our output here. I'm sharing it. So when you take the output and then you come to you have to check the histogram first, what you can easily use your eyes to see. You could tell that this particular side is approximately the same as this particular side. So that means this particular data is normally distributed. And in otherwise, it looks like this. The graph we have here looks like this. It looks like the normal distribution, the one in the middle. So our output or our cumulative curve graph, that is how our histogram here looks. So now when we check this one, we can easily tell that the data set is normally distributed. So you could see our mean being 70. That means when we put all the weight of the people together and distributed it equally among them, each and every one of them is likely to weigh 70.24 kg if the unit is in kg. With standard deviation, that is, the spread is not much, with standard deviation of 12.224. So if it happens this way, and then this one here, the n here, is our sample size. So if it happens this way, it means it is normally distributed. But you don't end it with the histogram. But you go here and then use the statistical evidence. So now when you get to the test of normality, that is our statistical evidence, then you check our sample size is 200. For that matter, you use the Shapiro-Wilk. Even though this and that, they all speak the same. But when you are doing your research or you are defending your thesis, emphasize on this side because of the sample size. Panels are likely to ask you, this side there is significance, this side there is significance. Why just paying attention to this side? Your justification is that if the sample size is less than or is 50 or low or below, sorry, 50 or below, then you use the Kolmogorov-Smirnov. If the sample size is more than 50, then you use this one. So in our case, since our sample size 200 is more than 50, our emphasis is this one. So 0.912. And for that matter, since this one here is is greater than 0.05, it means that our data is normally distributed. So let me check the statistical evidence side. We said if p-value is greater than 0.05, it means that the distribution is normal. And for that matter, we use parametric test. Otherwise, so in this case, weight is normally distributed because we had our statistical test as 0.912, which is greater than 0.05. So that means we go by this particular side. So with the income, we go by this side because our statistical evidence is 0.01, which is less than 0.05. And for that matter, now we check our various objectives. So when you finish with these particular two things, that is when you now look at your objectives to tell as to whether you use parametric or non-parametric. For example, if someone is running the analysis and his objective is to examine the relationship between two continuous variables, or maybe income and weights, then the person is likely to pick correlation. But you have to be very sure whether correlation will satisfy. Sorry, it's about correlation. But the correlation, we have two measures. We have Spearman and then Pearson. So, but mostly, most people, when they are going to do correlation or to determine relationship, they go straight for the Pearson's correlation. They don't check the normality. And this one goes against the quality of your results. So mostly you have to be very sure. So now we now understand both the parametric side and the non-parametric by using the normality. So now this one, for instance, if we want to check or we want to examine if there is more weight. So now I explained to you that when we finish, if I finish with the normality assumption, we are going to start with the parametric test phase before we move to the non-parametric. And now let me check it. Our parametric, we can compare the mean of one sample t-test. That means we are going to compare the mean to a specific value, or we compare more than one group, or we compare related or paired samples. So we have to use this particular data to check it. So now let's go back to the data. So in this case, in case we want to find out if the weight, now our weight is normally distributed, we all have confirmed it, that it is normally distributed, and we have to use the parametric. But we want to check if weight, when we check, our mean weight was 70 point something kg. So we want to check if the mean of weight is significantly different from 60. So because we assume that most people should be weighing around 60. Most adults should be weighing around 60. So we want to now compare. This 60 here becomes a benchmark. So we want to compare if the weight of these people, the mean weight of these people, is significantly different from the benchmark. That is the set value here. If it is significantly different from the 60 we are setting. So how do we do it? That means if we have something like that, we call it one sample t-test. So we are going to do the one sample t-test, trying to compare the mean of that particular group. So what you have to take notice is that we are dealing with one group. And that group, we are taking its mean, comparing it to a benchmark, a particular value. So it's not like more than two groups, it's just one group. We are taking the mean of that particular group across, or comparing that mean to a particular value. So this is how we do it. We go to analyze. Then we choose compare means. Compare means. Then you select one sample t-test. One sample t-test. Then we select it. We are interested in the weight because mean is, I say mean income. We use income for the non-parametrics. So I want to deal with the weight first. So you push this one to the test variables. And then now you come here and say test value. So that is where you produce your benchmark. So we assume that most adults are weighing around 60 kg. So you put the 60 here. You don't need anything here. You don't need anything from the bootstrap. So what you do is when you set that value, that's the only thing you have to do. And then you say, okay. So now when this value here, when the result is being produced, this one is just descriptives. It's just describing what the data is talking. So this is the mean as we just did earlier. And this is a standard deviation. So what you should be interested in is here. Now, this is our test value. Please, can you see my screen?
No.
Sorry about that. Usually when I produce output, it moves in a different window and the zoom does not reflect it unless I reshare it. Sorry about that. Can you now see the output?
Yes.
So when the output is being produced, this side here, one sample statistics. This side is just describing it, just the descriptives, it's just like the descriptive statistics. So we have our mean and then our standard deviation, just describing the important features. And some of the important features are the mean and then the standard deviation. So this is where your real test is. So with this one, the t value here can be used to make a decision. But usually this one, we always calculate it from the table. Sorry, from the data, we calculate it manually using a pen, a paper, and then a calculator. So, and that is not what we are doing here. And after you get the results, you compare it with something we call a table value. And then we will make a decision. In this case, this value here should be greater than what we have in the table value to make it significance. So, but mostly we don't do it that way. We use the computerized one. And when we are using the computerized one, we choose a significance. That is where we have the SIG. That means the significance. And that is what we use as our p-value. So what we do is our p-value should always be less than 0.05 for it to be significant or statistically significant. It should be less than 0.05. So now in our case, our p-value here is 0.001 is less than 0.05, which means that we can confirm that the mean weight, if it is students or individuals, the mean weight of the individuals is significantly different from 60 kg. And now this is the mean difference. We use the 70 here, the mean, and then subtract the 60 from it, we get this value. And then here is telling us the confidence interval of the differences here. That means 10.24. The difference is 10.24. So if you want to report here, you will say that we are 95% sure that the true difference of the mean weights and then the true difference of the mean weight and the assumed mean weight, this one is the assumed one, it can lie between or lies between 8.54 and then 11 kg, which means that within this range, you can find 10.24 or 10.245. That is how we report here. So when we finish, I will take time and then put it in Word report and then send it to the group so that you can practice with. But as I told you, let me have your homework so that I confirm whether you are really doing well or you are following. So it's not anything used to punish you, but I just want to be sure if you are really doing well or you are really following what we are learning. So now, please, do you have a question with this? So this one can be, the objective can be like to examine the extent of the difference between the mean kg and then the test value. So mostly, most of your thesis, when you have your objectives, especially the Likert scale, they always say to examine the extent of facility management practices. Let me use that particular data because that's the data I worked on recently. So that one, you have strongly disagree, disagree, neutral, agree, strongly agree. So you use a neutral and you make comparison. So that is this one here now also looks like neutral in this case. And the neutral is the assumed value. So now let's now check if we want to compare whether there is mean difference in weight of males and then females. We now want to check if there is a mean difference between or mean weight difference between males and females. That means that we are now comparing this particular one between two groups, and group A is male, and then group B is female, or group 1 is male, and then group 2 is females. And then since we are comparing this one, the means of this one against this particular group, we use something called, we go back to the parametric. I just want us to be reflecting on it. Independent sample t-test. So I'm showing you. Compare means of two independent groups. So if the groups are just only two, then you use independent sample t-test. So let's go back to the data. So we have our data here. So now we want to compare if there is weight difference between males and then females. So we go to analyze, compare means, and then you select independent samples t-test. Independent samples t-test. So we select that one. Now we pick our weight and then put it here. And then because we are comparing it among some group of people, we put a group in the grouping variable. So you have to tell SPSS the group numbers. So you come here, define. You see, when we push gender here, it gives two question marks. Question mark 1, question mark 2. So you come to define, and then you put the group 1 as 1, group 2 as 2, and then you continue. That means you just define them. Then over here, you don't need anything. Bootstrap, you don't need anything. Then what you do is you say, okay. So now you come to group statistics. The group statistics here is just to give you an overview of or descriptive measures of the means across the groups. So the males and the females. The males are 115 and the females are 85. This is the mean weight of the males. The mean weight of the males is 71.
Please, we cannot see.
Sorry about that. Thank you for drawing my attention. So now this is, please, can you see it now?
Yes.
Thank you. So this is the output. So we have our mean weight. Sorry, you come to the group statistics here. It's just giving you the descriptive measures of the data. So we have our male and then female. These are the groups, the two groups. And the N here is just giving you the number of members in each group. So in group 1, which means the number of males, 115. And then the number of females, 85. Then these are the various means. the mean weight of the males is 71.82 kg. So let me say 71.83 kg. And then the mean weight of the females, 68.10 kg with their respective standard deviations. So with the males, it has more spread out. The weight of the males are more spread out than that of the females. The greater the standard deviation, the more spread the data set, and the vice versa. So when you finish here, this one here is just telling you the spread of the distribution. Now over here too, then you use this the independent sample t-test. So when you come here, we have something called Leibniz test for equality of variance. So this one is just to tell you that if equal variance is assumed and then equal variance is not assumed, what it is trying to tell you is, are they, even though we are comparing the means, but are the spread or the variances also the same? So one way to do it is we use something called Leibniz. So the Leibniz, it is just assuming. So over here, it means that the variances are almost the same. They have similar spreading. So we have to use this one. But mostly we don't report this side. Yours is to check if there is mean differences among males and then females. Even though you could see the mean of the males being higher than the females, but we want to check if it is statistically significant. And for it to be statistically significant, we always use the 0.05. So if our p-value is less than 0.05, that means it is statistically significant. And for that matter, we can say that the males are statistically heavier or significantly heavier than the females, and the vice versa. So when we come to our p-value, that is our significance. So usually when you run, SPSS will not give you p-value itself, but bear in mind that your p-value is the significance with a two-tail. So you pick this one here because we assumed equal variance. You could see that we have another significance value down here. We don't use this one, we use the one on top. It assumed equality of variance. For that matter, we use this one. So when it happens that way, this value here is less than 0.05. And for that matter, our test is statistically significant, which means that, and if it is statistically significant, how do we conclude? The males are significantly heavier because weight is talking about heaviness. So mostly when you are interpreting statistical reports, you need to understand the descriptive measures. So here is just the mean. So the mean weight of the males is statistically higher than the females, but weight is talking about how heavy or light someone is. So the males are statistically or significantly heavier than the females. So that is mostly or basically how we interpret statistical measures. If it is age, we will say the males are significantly older than, because it's now talking about old. So mostly statistical interpretation, you just need to be practicing. It's not like a method, but you need to understand the measure, like the variable you are working with. How then do we use the terms in it? So if it is age, we use older. This person is older than the other person. If it is weight, this one is heavier than the other person, or this one is lighter. So in otherwise, if we don't want to say the males are significantly heavier than the females, we can also say the females are significantly lighter than the males. In all cases, it is accepted. Please, do you have any question here? Do you have any question here? Okay, silence means we don't have a question. Now let's go back to the data. In some cases, I just want us to do something here. Maybe we want to check someone is, these people, we want to find out, maybe our objective is they just introduce some drugs that people should take in order to reduce weight. People should take the drugs in order to reduce weight. So I just want us to enter any data on our own. So I will also enter my own. So we just want to, you come to the variable. We want to see after taking the drug, whether there is significant reduction, or let's also say, maybe we just brought in a counselor and the counselor spoke with the student how to manage their weight. After the counselor has spoken with the students, so that they wouldn't be more heavier in order to become obese. So after the counselor spoke with the students, they now started following the counselor's instruction. So has the counselor's input has significance in the student's weight? So for that matter, this is the weight before the coming in of the counselor. We now want to see, or if we want to also use the drug. After the student, this happens to be the weight of the students before taking the drugs. Now we have given them drugs that they will take in order to reduce weight. So when they took the drugs, what happens to the weight? We now record the second weight. So let's do it on our own. If you want to, let's all use the same data. So you come to variable view and then create, let me call it weight 2. Weight 2. If you have the data, you can also change it that way. You can add another variable called weight 2. So this one, we are entering our data on our own. So I'm going to enter like 20 data set and then just copy and then be pasting. So if you want, we can use the same data set as I'm entering. Maybe 71, 67, 82.3, 66 point 57.9, 72, 90, 66, 65, 65 again, 63.2, 55. These are our current weights after the counselor met us. 74, 54.9, 65.5, 55, 76, so 69. So 20 here is okay. So I just want to copy the 20 and then just be pasting again. So over here, you just paste. And then I go down and paste again. Just be pasting where it ends, you paste. Otherwise, if we are entering it individually, we will not finish today because it's 200. Please, have you finished entering your own? So now, if you finish, then let's move on. So we now want to compare. These were the recorded weights after the intake of the drug. And then, sorry, these are the recorded weights before the intake of the drug. And after the intake of the drug, these are the new weights. So we want to see whether the intake of the drug has significant influence in weight reduction. For that matter, we can advise the students to keep taking that particular drug. Otherwise, we can tell them to stop. So this is one way we can make a decision with the data. So what we do is we go to analyze and then compare means. So over here, you will see paired sample t-test. You choose paired sample t-test. So it's just the same measure, but on the same individual. So this same group are the same as this, just that we apply some medicine. And this is what we had from them. And after they took the medicine, the same people, this is what we had from them. So we use a weight before the intake of the medicine and send it to variable 1. And then we select the second one here and then move it to variable 2. Automatically it will go to variable 2. Now you don't need anything here. You don't need anything at the bootstrap too. So what you do is you just say, okay. So now this is the first weight. The weight before the drag and the weight after the drag. That's the paired. So the weight before the drag. So the mean weight before the...
You can't see the results.
Sorry. I noticed that. So I'm sharing it. So after this, please, can you see now?
Yes.
Okay. So after the intake of the drug, these are the various means. So before they took the drugs, we have the weight was 70.23 kg. And after they've taken the drug, the weight has now reduced to 67.88 kg. So now we want to check. Here is just like correlation. We want to check if there is correlation between or relationship between the intake of the drug before and after the weights before and after the intake of the drug. So here our correlation is inverse. So as we keep taking it, our weights are reducing. So as this one is increasing, this one is reducing. That is what the inverse here means. And then here is the significance. Yes, there is significance, but this is not what we use in making our decision. So we want to check the mean difference is you use this one and then subtract this. And then our paired sample t-test will produce the mean difference. That is what we have here. And then we match it to the significance. So the value here. So the significance here, that is our p-value. This and that, like I explained to you in the independent sample t-test, they perform the same thing. So over here, you just select this one and then compare it to 0.05. So if this one here is less than 0.05, that means it is significant. Otherwise, it is not. So in our case, we had 0.025, which is less than 0.05. And for that matter, we have enough evidence to conclude that the introduction of the medicine or the drug has significantly changed the weight of the students. In order to say, have significantly reduced the weight of the students. That is to say, in interpretation, you can use it the way you want. That is to say, the students are significantly lighter after the intake of the drug. So interpretation, it doesn't have a method, but you have to use your grammar and then relate it to the variable of interest and then statistical measure too as well. Please, can we have 5 minutes break?
Yeah.
All right. So by my time, it's 7:01, so we are coming back 7:06. the paired sample t-test. So this one is just like something has been introduced. You've taken measures on some particular people, and then, or maybe just a way of motivating students. This could be the scores of students. The weight here could be the scores of the students. By then, you now motivated them by giving them some incentives, telling them that if they are able to perform very well, you are going to give them this. So that means you have introduced something on the same students, so you have taken their performance before the motivation. And after you have motivated them, this could be the performance after the motivation. You can also compare. So whenever you want to do something on the same sample, but something has been introduced, which has been performed, or the variable has been taken 2 times, that means you use paired sample. This is the variable in one way, and then this is another variable after something has happened, but on the same people. So now, if it happens that way, you go by the paired sample t-test as we did. So you come here and then just get if there is a significant change after the introduction of the thing. So mostly, if you want to explain this t-test, you would say that the mean value of, then you quote that particular variable name, is significantly different, if actually it is significant, from the benchmark, which is, then you quote that value, as we use 60 as a benchmark. Then you just report, adding your own grammar. So our next thing to do is the t-test here. It is performed on one group. It can be performed on one group to match the mean of that group to a particular threshold, or sorry, a particular benchmark. Or you can compare the mean of that particular group, variable, to more than, to 2 groups, not more than, to just 2 groups. Or you can still take the mean of that particular group before and after the introduction of something. So these are the ways we use the t-test. So the first one is one sample t-test. That is when we want to compare the mean to a particular value. We use the one sample t-test. When we want to compare the means across 2 different groups, like we did comparing the means between males and females, that one we use t-test of independence. And when we want to check if something has been introduced and we are taking the weight again, and then we try to compare before and after the introduction, then we use paired sample t-test. So please, you have to know where we use each and every one of these. And they all fall under the parametric test. So these are the ways you always justify your results. Now, what if the groups are more than 2? For example, we have our age group. What if this one is more than? We could see that some people are less than 20 years, others are within 20 to 29 years, others are within 30 to 39 years, others are within 40 to 49 years, and then 50 years and above. So when it happens and we want to compare their means, we cannot use the t-test. What we can do is call ANOVA. So that means when the means are 3 or more than 2, when we want to compare the means among more than 2 groups, we use what we call ANOVA. So ANOVA is an extension of t-test. T-test has its ability, or is being limited to only, the highest t-test can go is comparing between 2 variables. But when it is more, t-test cannot work. And that is when we introduce ANOVA. So ANOVA can now also take from 3 and above, 3 groups and above. So for that matter, let me explain. When you run the ANOVA test first, and then if it is not significant, you end it there. Please, I'm taking it again. When you run the ANOVA test, we always compare the p-value to 0.05. So to check if it is significant or not, like we did earlier. If it is not significant, we end it there. We don't do any further test. But when we perform the ANOVA test and it is significant, then we have to move further to tell where the differences or where the significance value lies. For example, let me make it clearly here. We are now going to check the mean weight among these age groups. So assuming we run the ANOVA and we notice that it is significant, when it becomes significant, it will tell you that what it is trying to tell you is that, yes, there is significant difference in the weight across age groups, but which particular age group is actually different? So it is just trying to tell you that at least one of the age group is different or significantly different from the others, but it will not be able to point to you where the differences is or where the differences lies. And for that matter, if ANOVA tells us that there is significant difference at least among one of the age groups, then we have to dig deep in order to check where the difference is actually coming from. So when you perform the normal ANOVA, if it is not significant, then that means there is no differences among them. But if the ANOVA result shows that it is significant, that means we have to dig deep because it will not tell you where the difference is. The difference lies. It will not tell you whether 30 to 39 is different from 20 to 29, or 30 to 39 is different from this. It will just tell you that there is difference among them, but which of them is different from the other. So that is basically how ANOVA works. So if it is not significant, we end it at the ANOVA. But if it is significant, then we have to do further tests in order to reveal where the difference lies. So let's take it from here. So now let's go back to the data. We are going to perform the ANOVA. Like I said, it is an extension of the t-test. So we move to analyze. Compare means. We still use the compare means. Then we select one-way ANOVA. One-way ANOVA. So we are interested in the weights. And then we push the weight to the dependent list. So when we do, we push it to the dependent list. And then we come to age group. And then we push it to the factor because we are comparing it across the various age groups. We cannot use gender because gender has only males and females, and ANOVA takes more than 2. So now we come to options. When we come to the options here, then we check descriptives because we have to see the mean for this descriptive. We are checking it because we have to see the mean weight for people who are less than 20 years, the weight for people who are within 20 to 29 years, the weight for, so we want to see the mean weight for each and every one of the groups. That is why we are checking the descriptives with their standard deviations. And then you also check homogeneity of variance tests. So homogeneity of the variance test, we want to check if their variances or the spread in the weight is similar or is assumed to be similar or not. So that is what we say, the homogeneity of variances. So these two things are needed here, the descriptive and the homogeneity of variance test. So when we run, we have to consider the Leibniz. So let's continue. And these are the only 2 things we need from here. Then we say, okay. And this is our output. So now, when we come to the descriptives, you realize those that are less than 20 years, they have their mean to be 73 points, their mean weight to be 73.13 kg. Those within 20 to 29 years falls within 70 to 13 kg. And then those within 30 to 39, 70 to 3 kg. And then those within 40 to 49 have their weight within to be 68.25 kg. And then those within 50 and above are just 70.83 kg. And the NN here are the number of people in each particular group. So those less than 20 years, they are 19. Those within 20 to 29 years, they are 86. Those in that order. And then these are their various standard deviations. So these 1, 2, 3 are the things that are very necessary here. Then when we come to homogeneity of variance, let me come here first. Let me go to the ANOVA. So at the ANOVA here, you check. Then when we check, we have to check the significance here to see if there is significant differences in the weight. But the ANOVA here tells us that it is not significantly different. And for that matter, we don't have to do further tests. We end it here. But I don't want to end it here. So I will use the income, even though the income is not qualified for here. But for the purpose of our teaching, I just want to use it to show you how we do the further test. So if you get it here, this one is telling you that there is no significant difference among the in the weight of or in the mean weight across the age groups. There is no, this one here is telling us 0.770 is greater than 0.05, which is saying that it is statistically not significant. That means in research perspective, we end it here. Otherwise, we have to do further tests. So in research perspective, we cannot continue. We have to end it here. But most cases, it should be significant. And when it is significant, we have to do further tests. So let me use the second weight to also check. If it is not significant, for the sake of our learning, I have to use the income. I did not actually want to use the income for parametric, but because it is not normally distributed, but for the sake of our studies. So now let's use the weight too. This one is just the normal weight, and then follow the same procedure. So let's go back to the data. So I'm now going to use this particular weight to check if it is significance. So we go to analyze, compare means, and then one-way ANOVA. So I take this one out here, and then I take the weight 2 inside, and then still compare it among the age groups. We have already come here, and then we check the homogeneity of variance test, so it's enough, and then the descriptives. This one too is not significant. Let me share the outputs. So the output here too is not significant. So when we just get it, we come to the ANOVA phase to check if it is significant, but we could see that it is not. So I want to use the the income to do the same thing, even though the income is not qualified, because checking the normality, it is not normally distributed. but I just want to use it to show you. So when we end it here, if at the normal circumstance, we have to end it here because the weights are not statistically significant. The mean weights of the people are not statistically significant across the age groups. So let's see. We are going to take the income. So I'm going to compare the mean income across these age groups to see whether there is significantly different in the mean or in the earnings of the people based on their age categories. We go to analyze as usual, compare means, and then one way ANOVA. And then I bring this one out and I take the income in. We come to the option, the descriptive and the homogeneity of variance. So we say, okay, let me check if this one is significant. Oh, this one too, there is no significant difference. What do we do? What do we do? Please, let me look for different data sets. Let me look for different data sets. I think after that, I will share that particular data set with you. Because I just want to get significance value. Please, can you see the data set I shared right now? Can you see these data sets?
Yeah.
Okay. So this one is gender. And then we have ages. This one is about exams. So these are the scores of the students. And then these are their various stress level. These are the stress level. This one is about the stress the students are going through. So if it is low, 1 is low stress, 2 is 1 is lower, 2 is low, 3 is neutral, 4 is high, and then 5 is very high. And then after the introduction of a counselor, these are also their various stress. So to compare, and then these are, since they are students, these are their exam scores. So we want to check based on the one-way ANOVA. We want to check if the student's performance is different across age groups. So let's see if this one will be significant.
Please, did you share the data set on our page too, on our WeChat?
I will share it with you.
Okay.
Yeah. So now we go to analyze and then compare means one-way ANOVA. So we have our scores, that's our exam score. We put it in the dependent list. And then our ages, we put it in the factor. And then come to the option and select descriptive and then homogeneity of variance test. And then we say continue. Then we say, okay. Now let me get the output. Let me share the output. Can you see the output?
Yes.
So good. I think this one is significance. So now when you come here, you could see that the p-value here, the significance value here is less than 0.05. That means the performance of the students, the mean performance of the students is different across their age groups. At least one of the age groups perform differently from the others. So over here, ANOVA is just telling us that at least there is one of them that is statistically significant. But ANOVA will not reveal. That means one or more of them may be statistically significant. But over here, it will not reveal where the difference lies. And for that matter, we need further tests to reveal the difference, where the difference is coming from. The one we did earlier, if we get it 0.0, sorry, greater than 0.05, we just have to end it there. But this one is requiring us to do further tests. So now let's come to the various means. These are the number of people in each category. These are their means and the standard deviation. So those less than 20 years have their mean score to be 63.17, or let me say 63 marks, approximately 63 marks. Those within age group 20 to 29 perform or score, have their mean score approximately 73%. And those within the age group 30 to 39 have their mean score approximately 79%. And then those within the age group 40 to 49 have their mean score approximately 70%. And then the overall mean score is approximately 73.3, or sorry, it's approximately 73%. So now over here, we want to check homogeneity of variance, whether they assumed the same, whether they have this, they assume the same spread, this side, whether this side, this one here is just telling us the means. This one is talking about the variances, whether they have similar variance. So what you do is, when the results is being produced here, you check the significance value here. But in this case, we are interested in the mean. We take the variance against the mean. So we trace it based on the mean. So if this value here is greater than 0.05, that means they assumed equal variance, or we have something called the assumption of equality of variance. So here, the assumption of equality of variance is met. Otherwise, that is to say, if the p-value here is less than 0.05, that means the assumption of the equality of variance is not met. So why is this one important? The reason why this one is important is that when we want to do the further test, if it assumed equality of variance, then in the further test, we are going to use the post hoc. And then when we are using the post hoc, it has assumption of equality of variance and then inequality of variance. So if it has assumed equality of variance, we are going to use Techie HSD. Otherwise, if it is the assumption of equal variance is not met, then we are going to use Game Howells. So when we get to that side, I will explain all of them to you. So this one here is just trying to tell us the statistical value we have to use when we are doing the further test. And that is why this one is also very important. And that is why I did not explain to you when this one was not significant. So when this one is significant and you want to do further test, this one too will tell you the test you are going to use. So whether they assume equality of variance, or if the equality of variance is met, then what do you do when you are doing the further test? Otherwise, what must you do? So basically, that is the role this one is playing. So now it is significant and we need to do the feather test. And we also know that the assumption of the equality of variance is met. That means we assume the same variance for them. So now we are going to use the post hoc Tiki HSD. They are all post hoc, but under post hoc, we have various measures. So this one will inform you which of the measures are you going to choose. So now let's move on. Which data was I working with? Good. Let me share the data again. So we are back to the data. We have now seen that at least the scores differ in terms of age. One of the age or the scores is different. At least one of the age is statistically different from the others. So we are now going to dig deep to find out where the difference lies. So we go to analyze, compare means, the same one-way ANOVA. One-way ANOVA. And then we have our scores, their performance, and then our factor as we did. This time around, we come to post hoc. You use this one, post hoc. That is what you are going to use to do the feather test. So now when you come here, you have seen a lot of tests. Which of them are you going to take? You have to take at least one of them. Over here, equal variances assumed. These are the various tests. And over here, equal variances not assumed. So, but mostly the most popular academic one is the Tiki HSD. So in our case, it has revealed that the equal variance or the assumption of equality is met. That means equal variance is assumed. So we have to use the Tiki. Otherwise, if it is not, if the equality of variance is not assumed, then we come here to select games Howell, but it has assumed, and then we use Tiki from this side. And then we say, okay. And then we say, okay. So now we have gone through the descriptives. This one is not necessary here. And then the ANOVA, these are the our previous results that we had. So we don't
can
need
see
them.
the results.
Sorry, let me reshare it. Please, can you see the results?
Yes, yes.
So these are the ones we had when we just did the first test. So to reveal that at least one of them is statistically significantly different from the other. And this happens to be the test of homogeneity of variance, which revealed this one. So now, this is what we are going to use, the multiple comparisons. That is to tell us where the significance lies. So this one here, you see the Teki HSD that we chose. So sometimes in your research, maybe you have done the multiple comparative comparatives, and then you have used the Teki HSD. Someone can ask you, why did you choose to use the Teki? Because if the person is much enlightened to statistics, the person knows that we have other measures there. So why did you choose this one? That is when you are defending it. So you have to let them know that this particular one has informed that decision. So this one, since the Leibniz is not significant, that means the equality of variance is met. And that is why you have to do the multiple comparative by using the taking. So what this one over here, what it does is that it takes each and every one of the ages and compare it with the others. So first, it takes the age less than 20 years and compare it with age 20 to 29 years. So then you check this one, this is the mean difference. So that means to take the mean age for this one minus the mean age of this one. So you get negative. But when you come here, it means it is statistically significantly different. So in that case, you can say that this one here, this age here, is statistically significant different from this particular age. So the mean score, so these people here, their results or their performance, their mean performance is significantly different from the performance of people within this age group. And then we compare the same age group to those within 30 to 39 years. This is the age difference. And it also shows statistically significantly different. That means these people perform better than them. These people too perform better than them. So, and then the difference is significance. So, which means that these particular groups, they learn or they perform far better than this particular group significantly or statistically. Then you compare the performance of this particular group to the last group. And then this is the mean difference. But when you check, it is not significantly different because 0.334 is greater than 0.05. That means this particular one, the performance of people within less than 20 years and those within 40 to 49 years is statistically almost the same. There is no statistical difference. So they almost perform the same thing. So that means in this side, you have compared those within the age less than 20 or those below 20 years across the other age groups. So you now take this one and compare it across the other age groups. So already here, you've already compared 20 to 29. So over here, you don't do it again because it will repeat the same results. And now you take the 20 to 29 and then compare it to 30 to 39. You could see that this their performance. That means those within 30 to 39, they perform better than those within 20 to 29. Because this is the difference. And the difference too is significant. So those within the age group 30 to 39 significantly perform better than or higher than those within 20 to 29, which means that this particular group, they are serious in their academics or they perform better in terms of academics against the other age group. And then you take the 20 to 29 too and compare it with the age group 40 to 49. And then this is the difference. So that means the 20 to 29 is performing better than the 40 to 49, but the performance is not statistically significant. So this one too is not different from the other one. Now you take 32. You've already compared 30 with 29, 30 with, so now what you do here is you compare 30 to 49. And then you could see that this is the difference. But the difference is not statistically significant. So which means that those within the 40, even though these people, those within the 30 to 39, they perform better than those within the age group 40 to 49. But it is not statistically significant because 0.053 is greater than 0.05. So this is where your decision lies. This one is just describing the difference. Now you take 40 to 40, so you just end it here because 40 to 49 has been compared to almost all the other age groups. You are going to compare it with the 3 age groups, and then 20 to 29 has been compared to 40 to 49. To less than 20 years have also been compared to 40 to 49, and then so when you come, it's just like you are repeating the same thing. So I will put this particular one academic way. You don't repeat it like the SPSS has produced. So I'll put it in academic format and then share it with you in the group. So basically, when you want to compare more than one group, more than two groups, you use the ANOVA. And then when you run the ANOVA and you have noticed that there is it is not statistically significant at the ANOVA level, then you end it there. Otherwise, you have to do deep analysis or you have to dig inside to reveal where the differences is coming from. So basically, if this one here is not significant, we end it there. Otherwise, you go further to do this. So since this one is significant, then we move further to do this one. So that is how we work with the ANOVA. Please, is anyone having a question? So what we just did now is comparing of means. Is anyone having a question? Yes, Mauli Smarts.
Yes.
You can
So
ask.
with this, which of the age categories is now contributing to that significance level? Which of them now? Because we are across the categories, we have seen some being significant, that is 20 to 29 and 30 to 39, be significant when we compare with less than 20. But when we compare same with less than, when we compare same with when we compare same, we have seen that across we say we should end at 40 because that one is more. It's not significant. So which of the age variables or age categories is actually contribute to that significant value that we have observed at the ANOVA level?
So your question is asking which of the age group is contributing significantly into this output, right?
Exactly.
What we are trying to do is, it's not about their contribution, but we want to see if there is differences in their performance. So when we run the analysis, these are the various means. So we could see that this is the mean of this is the mean for this particular age group, this is the mean for, but are they significantly different from each other? So ANOVA here is saying that at least one of the age groups performance is different from the others, but it will not show us which one is different. Please, do you get it? Then if we find out that yes, at least some are different from the others, then we do further tests to see where the difference is coming from. Over here, it's not like their contribution, but we want to see the differences. Do you get it? So when we come to the multiple comparative tests, this one will now be picking each and every one of the age groups. So in that case, when you take age 40 to 49, you will realize that it's not significantly different from any of the age groups. So this one here performs similar to the other age groups. So this one is out. When you take those within the age group less than 20 or the younger people, they perform significantly different from those within the age group 20 to 29 and also perform significantly different from this particular group. So they perform significantly less than those within this particular group. Because when we compare, that means you are taking the mean of this one minus the mean of that. If it gives you negative, that means the one here is performing better than the one here. If it is positive, it means the one here is performing better than the one here. So all are negative. So that means across all the age groups, they are performing better than those within the age group less than 20 years. However, the differences, they only have significant difference with age group 20 to 29 and then 30 to 39. So they perform almost the same with those within the age group 40 to 49. And that is why we have our significance value here. Please, do you get it? So in that case, our further test revealed that age group those within the age group less than 20 is their performance is significantly different from those within the age group 20 to 29 and then 30 to 39, but not different or significantly different from those within the age group 40 to 49. And then we take the 20 to 29 too and compare it with the various age groups. It has already been compared with less than 20 years. So we are now going to compare it because it's been compared with those less than 20 years. We are now going to compare it with the 30 to 39 years and then 40 to 49 years. And we could see that those within 30 to 39 years, since it is negative, they are performing better than those within 20 to 29 years. And then the output is also significant. But when you compare it with the 40 to 49 years, the p-value is not significant. So this one too is significantly different from 20 to 29, sorry, less than 20 years and then 30 to 39 years. Then we use 30 to 39 years to compare. We've already used the 30 to 39 to compare with 20 to 29. 30 to 39 has already been compared with less than 20. So the only thing we are going to do here is to compare the 30 to 39 with 40 to 49. And we could tell that even though there is difference, but the difference is not significant. So with the compare means, we are just going to reveal the differences and not their contribution, whether the differences is significantly different. And when we say significantly different, it means that the output that we are seeing or the differences that we are seeing did not just happen by chance. That is basically what it means. The differences that is being displayed is not just happening by chance, but in all cases, that must be the case. So this one is just a way that I prepared my own data. So yes, Belinda.
Yes, I got that before Belinda comes in. I got that. But you see, when we're selecting the post hoc text, we have Turkey B also there, but we chose Turkey HSD. Is there any
Okay.
reason for that specific?
You know, the Techie HSD is just the basic academic acceptance one, the most widely used.
Okay, thank you.
Yeah. Yes, Belinda.
Yes. Please with the significance, 0
Please,
point
can you raise your voice a bit louder?
for determine the significance. I'm looking at the
You say,
0.5.
please,
Point zero. Can you hear me? Hello?
I can hear you now. Yeah.
The point 053.
Okay.
Yeah, I think you reported it as not
Not,
significant.
yes.
Yeah, so I want to ask, this is almost like a borderline significance because someone might
So, you
report
know,
it.
the threshold is 0.05. Any value greater than 0.05 is not significant. And then any value from 0.05 and below is significant. So once we have something added to the 0.05, that means the 0.053 is a bit higher than 0.05. And that means it is not significant. Please, are you okay now?
Okay.
Even if it is 0.051, it's still not significant because that value is greater than 0.05.
Mm. So I'm asking
So
because
it is only significant when it is 0.05 and below.
so in reporting it, we have to report in 2 decimal places or 3 decimal places.
You have to report it in 3 decimal places.
Mm.
You know, mostly, especially the significant values, mostly it is advisable that we report it in 4 decimal places. But most of our software that we use to produce, they usually limit it in 3 decimal places.
Mm.
So I know you are trying to say when you convert this, it will give us 0.05, isn't it?
Yeah.
But mostly we always report it in the standard form is 4 decimal places.
Okay.
Yeah.
Thank you.
So please, any other question?
Yeah, so what happened to you see there's some score beneath the table, the homogeneous subset down there. Those
This
results.
one,
There's
it's not important.
okay, okay,
That's why I did not go through that side.
okay.
This one, we are just preparing ourselves for our academics. So when you, this one, like when you want to run any of the tests, you have to find out what you want. So this one, we are just going to compare their various means to see if there is statistically significant difference. So what we do is we come here first, the ANOVA. If the ANOVA reveal that, yes, there is statistically significant difference, then that means it is requiring us to do further tests. And for the further test, we know that we are going to use post hoc. And then to do the post hoc, we come here, homogeneity of variance, to check whether the assumed equal variance or the assumption of equal variance is met. If the assumption of equal variance is met, then you have to think, which post hoc test am I going to do? Otherwise, so that means you are going to do multiple comparison. So which post hoc multiple comparison are you going to do? And then if the assumption of equality of the variance is not met, which one are you going to do? So that means your objective here is to do further tests to reveal where the difference is. So when you get here, that means you've ended your objectives. Please, do you get it? So this is
Yes.
where you want to reveal where the difference is coming from. And that is basically the scope of ANOVA. Please, any other question? Please, the homework you have to try. Don't send to the group. You send to me privately. I check, and then if I see improvement, I'll let you know. If I notice that maybe you are not doing it well too, I will just read through to see where the errors are coming from, and then I correct you so that you can do it yourself confidently, even if no one is guiding you. So that is basically the objectives of the homework. So please, let's try to all participate. Any other question?
Okay, you said you'll be sharing this data with us. So when you share it,
Yeah, I will
run it
report the
also.
outputs. I'll report the
Okay.
output. It is from here, I have to go and pray.
And,
So I will report the
and
output. Maybe tomorrow I share it in the group
and
before
the
our
data
next.
itself you use, yeah, the data that you use for this ANOVA one too.
Sure. I will do it that
Okay,
way.
okay. Thank
You
you.
already
Okay,
have
thank
the
you.
data for the other one, right?
Yes, Yes, yes.
So I'll share this data and then the output with
Okay.
you.
Okay. Thank you. Bye.
All right, you're welcome. So if there is no question, please, Madam Irene, can you come in to?
Okay, Doc, thank you so much for this this session. We really appreciate it in as much as you are not feeling well. And we hope you get well soon.
Thank
You have the next meeting is next week, Saturday, right?
No, tomorrow.
Oh, yes, you said tomorrow. Okay, so we'll meet tomorrow then.
Yeah.
Please have a good evening, everyone. And then check the chat box. We've shared the QR code for today's session's attendance. And the next session is also ongoing. That is Smart PLS. If you want to join, kindly move to that platform as well. Okay, so that will be all for now.